Listen, and today we will talk about another aspect of ferromagnets. So these are called as domain. Okay, so what is a domain? So basically, let's say, so the general description is that. So I think you have heard about domains in terms of magnetism. Okay, but the general definition of domain is that, let's say, if different regions of a macroscopic system break. Yes.
So your screen is not visible.
Screen is not okay. In
Okay, sir.
Somit, can you see it now?
From
Hello, Somit.
network issue from my side, I think.
Okay, so maybe you can disconnect and reconnect again. Okay. Okay. So what I wrote is that if different regions of a macroscopic system break symmetry in different direction, then one can expect singularities. Okay, so and these singularities, they arise in the form like domain walls, defects, vortices, dislocations. Okay, sorry, my writing is a little bit tilted in this slide. Okay, but since the first line is tilted, so the remaining ones also followed that, but I hope you can read it anyway. So basically what it says that for a macroscopic system, if there is a symmetry breaking in different direction, that means it is not isotropic anymore, then as a result of this some singularities arise. Okay, and that gives rise to things like domain walls, defects, vortices, dislocations. Okay, so domain walls will be explaining in details very soon. Defects you know already, right? Like if a material does not have its purest form, then there will be multiples of defects, or let's say vacancies, okay, that can create. Vortices you have probably heard about in the context of superconductor. Okay, I also explained little bit when I was describing the superconducting magnet. Okay, and dislocations. So dislocations are also like different planes of crystal, they get displaced, okay, randomly. Anyway, okay, so now what happens in the case of a ferromagnet? Okay, so in ferromagnet, the important singularity is domain wall. Okay, so this idea was first proposed by Weiss. So he first proposed this, basically the idea of domains. Okay, so what is a domain? Okay, so it's just that let's say a given material, let's say if it's a ferromagnet, then because of energy advantage, or let's say in order to save energy, this material will split magnetically into different regions, and these regions are called as domains. Individuals of these domains, they have a local magnetization. Okay, so each domain will have So let's say within which local magnetization reaches saturation value. Okay, but the direction of magnetization is different in different domains. Okay, I mean it does not need not to be parallel. Okay, ठीक है. So individuals of these domains will be separated by domain walls. Okay, so what we are talking about is that let's say this is a, let's say, ferromagnet. Okay, so there I will have multiple regions. Okay, okay, so there will be individual domains and within which locally there will be a specific magnetic direction. Okay, and these separations they are called as domain walls. Okay, any question on this? Okay, now in a ferromagnet at room temperature, saturation can be obtained using a small field. Okay, roughly 10 to the power minus 6 Tesla. Okay, and it is not possible for a paramagnet. Okay, why it happens? The reason is the applied field, it does not order magnetic moments individually, but just the domains to align. Okay, so this is done by domain wall motion. Okay, which is, let's say, energetically painless. Okay, similarly, let's say if we want to reach a zero magnetization state, to reach zero state, okay, at zero applied field, one, let's say, needs to randomize the magnetization of individual domains. Okay, so my handwriting has gone a little bit bad towards the end, but I hope you understood what is the essence of this, right? So is it clear what I wanted to say here? Anyone?
Sir, energetically painless
Okay.
meanings.
Means that it will cost very little or almost negligible amount of energy. Means that it will not cost a large amount of energy, which means that you don't have to provide or arrange an external excitation to provide you that kind of energy. Okay. What I wrote here?
No, sir. Totally
No, sir.
only, sir.
Huh?
50% only, sir.
50%. So which part is clear, which part is not clear?
Sir, that is the last one, sir.
Okay, so tell me what is a domain? What is a domain?
Sir, your voice was broken, sir, at that time.
Okay, what is a domain? Magnetic domain. Okay, thankfully you are here. Okay, tell me what is a domain?
Sir, in ferromagnetic material, there are the ferromagnetic material. There are small groups in which the orientation of electrons are same. That is called domain, I think.
You are making it too complicated. Okay, see, it's basically we have a ferromagnetic material, and this material it breaks up magnetically into multiple different regions. So you think of like a country like India. Okay, now it has different states. So each state is like a domain.
Yes, sir.
Okay, although if the states come together, they will form a country.
Yes, sir.
Okay, so all these domains they make the country, and the country is made up of the domain. So it's basically vice versa. Okay.
Yes,
Now
sir.
within each of these domains, we have a specific direction, or let's say one single direction of local magnetization.
Yes, sir.
Okay. Now why domains are important, or why domains form? It is because it gives some energetic advantage. Okay, what is energetic advantage? It means that let's say if the material does not form domains,
Yes,
then
sir.
it has to cost more energy, or other way, it will save more energy if it forms these small domains within the material, or if it breaks, if a whole material breaks up into small domains, then it will save energy. So it is energetically advantageous. Okay.
Yes, sir.
Now in a ferromagnet, what happens is that if we want to, let's say, saturate the material. Okay, so if you remember that in the hysteresis curve we have something here and then something here, right? So this is the saturation part. So if we want to saturate, then what we have to do is that we have to apply a very small field. Why? Because individual domains have, each one has their own magnetization. Okay, like this, right? So all I have to do is that these magnetization vectors I have to align in one given direction. Okay, if all are aligned in one given direction, I will reach saturation. Okay, right? So here I don't have to align individual moments in each of these domains. I just have to align the domain. which does not cost more energy. Okay, so that's why I wrote energetically painless. Similarly, if I want to destroy the magnetization state, or if I want to reach a zero magnetization state, then again I don't have to play around with each magnetic moments. All I have to do is that I have to randomize the domains, which means that these magnetization vectors of each domain have to be in random direction so that the total sum becomes 0. Okay, clear?
Yes, sir. Clear.
Okay, chalo. Happy to hear that. Okay. Now we'll talk about. So, is there any
Domain
question from others? Okay.
Hello, sir.
हाँ बोलो.
Yes, sir. I didn't get that important singularity part. I was disconnected. So can you please repeat that?
Slide this. Important.
Second slide.
Okay.
Yes, sir.
So I wrote here is that this is basically coming from like general perception or idea that if there is a symmetry breaking, but let's say within a system, okay, then different singularities can appear in different physical forms. So for ferromagnetic materials, it will be in the form of domains. Okay, let's say if it's
yes, sir. Yes, sir. Got it.
another material, let's say superconductor, then there will be vortices. Okay.
Yes, sir. Yeah.
Okay.
Got it.
Okay. Now we'll talk about domain walls. So what is a domain walls? It is nothing other than the boundary between adjacent domains. Okay. Now the domain walls are classified according to the angle between between the magnetization of two domains. Okay, so we have two different cases here. So let's say okay, so let me make it a little bit smaller here, otherwise I will be running out of space. Okay, so let's say this is one domain wall, so this is one domain and that is another domain, and here let's say this magnetization vector is like this, and in this domain the magnetization vector is like that. Okay, so between these two domains, if you see the magnetization vector, it rotates by an angle of 180 degree. Okay, so this is 180 degree domain wall. Okay, now there is another type where basically I have this and then that. Okay, so here the angle between the magnetization vectors is 90 degree, so it is called as 90 degree domain wall. Okay, so each of these domain walls, they separate magnetization vectors which are aligned by a specific angle. Okay, now go to okay, so now most common type of 180-degree domain wall is called as block wall. Okay, so what happens here is that the magnetization, it rotates in the plane parallel to the plane of the wall. Okay, so let me make it a little bit more clear. So let's say I have okay, so let's say this is a 3D view of my domain. Okay, okay, so now what happens here is that what I said is magnetization, it rotates by 180-degree in the plane parallel to the plane of the wall. Okay, so as you see that this is the plane of plane or the, let's say, domain wall. Okay, so what it does is that, let's say this is okay, okay, so let's say the initial magnetization vector is like this. Okay, then subsequently let's say it rotates. Okay, then let's say it rotates again. Okay, it becomes like this, and basically it keeps kind of like rotating, okay, along different directions, and finally on this plane, okay, it will become like this. Okay, so if you look at the initial state and the final state, the rotation between the magnetization vectors is 180-degree. Okay, so if I take slices along this path, then I can see the magnetization vector, it rotates by a small angle, so that the angle between the final configuration and the initial configuration is 180-degree. Okay, is this part clear? Your voice is breaking. Can you? Hello.
Sir, this is happening. Hello. Sir,
Yes.
this is happening in a particular domain.
No,
The
it is.
magnetization.
It is happening in the domain wall. Okay, let me make it a little bit more clear. So you see, this left hand side is one domain. Okay, I mean this up vector is one domain, and the right this down vector is another domain. Okay, so you have two domains here. Okay, hello.
Yes, sir.
Okay, so we have two domains here, and this part is separating these two domains, which is the domain wall. Okay, hello. Who is
My
asking?
question is like the up and down domains are present in two different domains, and the middle one is the domain wall. So in the 3D picture, in the 3D picture, from one domain wall to the other domain wall, there is rotation of the 180-degree rotation of the magnetization. So my question is, yeah, particular, that is that 3D picture you just drawn, it is denoting a particular domain in which the rotation is happening.
No, it's not the domain, it's the domain wall.
The total that total part is a domain wall.
No. Yes. Okay. So let me make it more clear. Let's say this is my initial vector in one domain. Okay. And let's say this is another domain. Okay. Right. Now, in order to change the magnetization vector from this to that, there has to be a 180-degree rotation.
Yes, sir.
Agree? Now this is a domain, let's say D1, and this is another domain, D2. Now these domains are separated by domain wall, right?
Yes.
Now what we are saying here, how this 180-degree rotation is happening across this domain wall.
Okay. So that the domain is thick enough.
Huh? Yeah, yes, domain wall has width. Yes.
Okay, sir.
Okay. I mean, wall needs to have a width, otherwise you cannot call it a wall. Okay. Okay.
Sir, I have a question, sir. What is the width of domain wall, sir? Minimum width.
What is the width of domain wall? Okay, so we'll come back to this later. So there is finite, it has finite width, and you can measure it. Okay, so it is related to certain other parameters. Okay, so it is related to the exchange constant also, and the anisotropy constant. So there is something else. We'll come back to this. Okay. Okay. So this is block type of wall, where basically this magnetization rotation is happening in a plane parallel to the plane of the wall. Okay. Now then there is another type which is called as nil wall. Okay. So here magnetization rotates in a plane perpendicular to the plane of the wall. Okay. So now if I draw a similar picture here, so what I'll see here is that, let's say this, then this. Okay. And here I have this, here I have that. Okay. So here what will happen is that, let's say the magnetization vector is like this, then it becomes like this, then it becomes like that, this. Okay. Similarly, you can. Okay. So the magnetization vector, it rotates in a plane perpendicular to the plane of the field. Okay. Okay. So this nil wall is clear, right? Okay.
Yes, sir.
Okay. Good. So now, in a ferromagnet, it costs energy to rotate neighboring spins. Okay, so let's say if we have two spins S1 and S2, which are at an angle theta with respect to each others, then it has an energy. Okay, so not then this is G. Okay, so it have an energy E will be minus 2J S1 dot S2. Okay, so this one you all agree, right? Okay, so this one I can write it as minus 2J S square cosine of theta, where basically mod of S1 equal to mod of S2 equal to S. Okay, so if these pins have equal magnitude, then this value will be minus 2J S square cos theta. Okay. Okay. Now for theta equal to 0, you will be minus 2J S square. Okay. Right. So theta equal to 0 means they both are, there is no angle in between them. Okay. So if I want to have a non-zero theta, then there will be an energy cost. Okay. So the energy cost for having theta not equal to 0 is approximately of the order of J SS square theta square for theta less than 1, or let's say when theta is very small. Okay, is this part clear? Anyone? Okay, so what I'm doing, let's say I have two spins S1 and S2, then there will be some interaction energy that is involved, right? So this is minus 2J S1 dot S2. Okay. So if the angle between them is theta, then this expression will come out to be minus 2J S square cosine of theta. Okay. Everyone agrees with that?
Yes, sir.
No. Huh?
Yes, sir.
Okay. So now what I'm saying, if theta equal to 0, that means there is no angle in between them. That means both are parallel, right? Or in the same direction. Then the energy will be minus 2J S square. Now from that, if I want to create an angle which is non-zero, then I have to cost some energy. Okay. So the energy that will be needed to do that will be of the order of this term, J S square theta square. Okay, so let me write it down probably. Okay, so the energy cost is basically delta E. So let's say E at theta equals theta minus E at theta equal to 0. Okay. So in the first case, or let's say in the other way. Okay, so it is minus. My pen is not working very nicely. Minus of actually it will not be minus, I think this will be plus probably. 2js square cosine of theta. Okay, so if I take this one minus 2js square, so this will be 1 minus cosine of theta. Okay, and if theta is small, so then this will be basically 1 minus theta square by 2. Okay, so this will be, so 1 will cancel, so it will be 2 js square times theta square by 2. Okay, so this will be j s square theta square. Okay, for small theta. Okay, is it clear? Okay.
Yes, sir.
Okay, so now in the case of a block wall, we know that, let's say there are n sides, so let's say over n sides, spin, rotate by an angle pi. Okay, right, so this is nothing other than this part. So I have drawn the slices, so let's say there are n such slices. Okay, so over n such spots the total rotation of pi happens. Okay, so now energy cost for having a line of spins is equal to n contributions of j s square theta square. Okay, where theta will be pi divided by n. Okay, so this value is basically j square pi square by n. Okay, right, now again, since in the case of a block wall, okay, we have planes of spins. Okay, so we are interested in sigma bw, okay, which is energy per unit area of block wall. Okay, okay, now in 1 square meter of wall, there are 1 by a square lines. Okay, where a is basically, let's say, the kind of like size of the wall. Okay, so a square is, let's say, the area. Okay, lines of spins. Okay. So in that case, I can write sigma BW will be J. Pen is what basically J S square pi square divided by n square. Okay. So now this will go to 0 if n goes to infinity. Okay. So what does this tells us? Anyone? Okay. So is this part clear what I wrote?
Yes, sir. Clear.
Okay. So sigma BW is basically is, let's say, the energy cost per unit area. Okay.
Yes, sir.
So what is happening is that this n is in the denominator. Okay. So what n here means is that number of such circles. Okay. So if number
very
of
large.
such circles are large or it goes to infinity, then this energy cost will be 0 or it will be almost negligible.
Yes, sir.
Okay. So what does that tells me? So let's say if I have one like this, okay, and the final one like that, and this let's say rotation, it happens over like, let's say, these many slices. Okay, 1 2 3 4 5. Okay, so there will be a finite energy cost that is involved for each of these flippings. Okay, but if this rotation happens over very small value of theta, okay, in that case the energy that is required to flip it from one configuration to other is almost negligible, because it is almost kind of a minimalistic change between neighboring configurations. Okay, is it clear?
Yes, sir.
Okay, chalo.
Yes, sir.
Is
Clear.
it to the quasi-static process we did in statistical
It's not
thermodynamics?
exactly the quasi-static process, but you can think it of in that term. Yes, the spirit can be same. Okay.
Okay, sir.
Yeah. Okay. So now it means that if a domain wall is formed, it will unwind. Grow in size
if suppose that if we have limited number of unwinding processor, that is the number of ends, then which wall is energetically favorable, sir? That is Niels wall, yeah, or Bloch wall, sir?
That you have to calculate from the energy expression. Okay.
Okay, sir.
Okay. Okay. Any other question? Okay. Okay then. Chalo. Okay, so we'll stop here. We'll start again tomorrow.